Welcome everybody joining this webinar about CWEX. CWEX, this webinar is going to be about transforming the industry with a revolutionary CO2 capture technology, which we call the CWEX technology. So thanks that you're joining. I have here today with me in the studio Erik van Dijk, and online Carlo Morelli will join us later as well. What can we expect today? Today we'll go through the past, present and future of the technology that we have developed. And we will try to make this webinar as interactive as possible. There will be two ways that we'll do that. We will have some poll questions that you can answer, but also there's the opportunity to ask us questions. And you can do that on the right bottom side. There is an orange button. If you click that, you can ask your question and they will come to me in the studio and we'll try to answer as many as possible. Like I said, I'm Soledad van Eyck and Erik and Carlo are joining me. I will introduce them further down the line of the webinar. What will we dive into today? We will talk a bit about the need for CO2 capture, but also how CWEX technology is actually working and why it's such an attractive carbon capture technology. We'll dive a bit into the history, and this is focusing on the larger projects that we did for CWEX in the steel making. Then we'll go to the current project Initiate, and we'll end with a perspective to the future. So, the need for CO2 capture. Before I start my storyline, I have already the first poll question for you. I would like to ask you what you think the role for CCS is to reach our climate goals. So I have three options for you, and there might be more, but I only have three. So the first one is that CCS is a transition technology that we need for the coming decades, but in the long run, we won't need it anymore. Or do you think CCS is an essential part to meet the climate goals, now and in the future? And lastly, it could be that you even think that carbon capture and storage should never be an option and that we will not use it. So, please fill in your answers. We will come back to the results of the poll question a bit down the line. So, this is me asking you this question, but of course I want to say what we as TNO and the people here think. Why do we actually need CO2 capture and storage towards 2050? For us, it's important to see where are CO2 emissions difficult to avoid. And we see that there's quite a lot of industries and sectors where it is actually hard to avoid CO2 emissions with other measures than CCS. So if you want to reduce the emissions there already now and in the coming decades and not wait until technologies are so mature, we need CCS right now towards 2050. But we think that even beyond 2050, CO2 capture and storage is necessary. And this comes from the IPCC report, where we state that if we want to stay below the 1.5 degrees climate, the warming temperature to reach that, you can see in this picture that we actually need negative CO2 emissions. And negative CO2 emissions you only can obtain when you do carbon capture and storage. So we actually think that it's very important. And here comes in the CWEX technology. So we think we have here a versatile and attractive CO2 capture technology. And I want to tell you a bit more about this. So CWEX is an essential element in our opinion in the energy transition. And what's nice of it is that it's really a platform technology. So today we will focus on the iron and steel industry because we're making some great steps there, but CWEX can actually be used for many types of industry. Everywhere where you have syngas type mixtures, you can use CWEX. So from the gas and oil sector, coal sector, everywhere where you have sustainable biomass sources. And with the CWEX technology, we capture the CO2, but we also produce blue hydrogen. We can use the hydrogen and CO2 for CO2 utilization, and when you use biosources, we can go to negative CO2 emissions. Well, how does the technology actually work? Because that's important. CWEX stands for Sorption Enhanced Water Gas Shift. And It is based on two things. First, the water gas shift reaction, where CO and steam react to CO2 and hydrogen. And secondly, it's the adsorption of CO2. Where the water gas shift reaction is an equilibrium reaction, by capturing the CO2, it is possible to completely shift the reaction to the production of hydrogen. And that works as follows. We have multiple columns, and they are in different stages of the process, which I will describe. First, we have the adsorption states. So we're at high pressure and high temperatures, and we're coming in with a syngas mixture. It can be a mixture in different forms, but we're coming in. Here we have the water gas shift reaction, so your CO is converted into CO2 and hydrogen, and your CO2 is simultaneously adsorbed on the adsorbent that we use. This means that on the bottom of the reactor we have the hydrogen product. At a certain point, the material we use is saturated, and we want to go to another column in adsorption mode. But the column that is saturated, we use the following steps. First, we have a rinse step where we rinse the column with steam. This is to get the optimal CO2 purity. Then we have a pressure equalization, which is very important for the efficiency of the technology, because with lowering the pressure, we can get another column that is at low pressure up to pressure. And this is also how the technology works. It's a pressure swing type of technology. While we have the adsorption at a high pressure, we do the desorption at a low pressure while we remain on high temperature. So with steam, we purge the column and the CO2 and steam will come off. And in this way, using multiple columns, we generate continuous flow of a hydrogen product and a CO2 product. So this is how the technology works in short. Before we dive into history, I want to come back to the poll questions, which are interesting and nice to see as well. So Erik, I will ask you something about that because we did not hear you yet. But when we look at the results, we see that 35% of the people think that it is really a transition technology, and 65% think that it's really needed also in the future. Can you share a bit what your opinion or view is on this? Where would you classify CCS?
I think indeed you can consider CCS technology as a transition technology, but in my opinion, it will definitely be something that is needed in the future as well. If we are going to a carbon neutral society, there will always be industrial sectors that are dependent on carbon. And so if you want to eliminate those emissions, you need CO2 capture. So in that respect, I think CCS technologies are required now to limit the carbon footprint of hard-to-abate industries, but they will also be essential in the future to come.
Yeah, okay, thanks. And maybe it's good to know for the people at home, but also for Erik and Carlo, nobody said CCS is not an option, which is maybe not strange seeing that you are joining this webinar, but it's still nice to see. So then we go into, we have no questions yet at this point, but they'll come for sure. I think my explanation on how the technology worked was very well. We go into the history a bit, because we've been working on Stepwise for quite a while. In this graph, you can see that in 2004, we started on lab scale. So we had around 2 grams of the material, and we were in the lab trying to see, does this concept work? And from there, we started really progressing. First, going within TNO from lab scale to bench scale, and at a certain point, we had a 6-column system in the TNO PETA facilities. But there's a point where you want to make the step to real industrial gases, and we made that step in the Stepwise project. Here we went to the first single-column TRL6 demo, where we really used steel gases. From Stepwise, we had other projects like FRESME and Initiate, which Erik will talk about later. But I want to tell you a bit about the Stepwise and the FRESME project, because they are finished projects, and we can show you a bit how the technology actually performed already in these settings. So we'll start with a small picture of the steel making process. What you see here is a very short compact version of how a steel plant works. And what you see is that you have your coke oven, blast furnace, and your basic oxygen furnace. And here is where your product, so your iron and your steel, is produced. But all these different steps within the steelmaking process generate gases. And these gases contain still a lot of energy, so CO, so they're syngas type of mixtures. So now these gases are used internally for different processes, and all the energy content that is not used internally is now often sent to a power plant to produce electricity. What we wanted to show is that we can capture CO2 from one of these lines and produce the hydrogen. So that's what we did in the Stepwise project. In the north of Sweden, of Luleå, there is the steel plant of SSAB. And next to this steel plant, there is the research facility of Swerim. And Swerim is the Swedish Institute for research around metals, let's call it metals. In the middle, you can see the installation we put up there. It's a 10-meter high column of 40 centimeters of 50 centimeters of diameter. And it was linked, and the gases from the SSAB plant were connected to it. How did the pilot look like? So to start off, we had the blast furnace gas. So 800 normal cubic meters per hour of blast furnace gas were used in the plant. It first goes through a pre-water gas shift section and then to the CWEX section. The CWEX section was the column I just showed. To show you, if the CWEX system would have been multiple columns, we would have been able to capture 14 tons of CO2 per day. So if we could made it continuous. So, to give you an idea what it looks like, here's some pictures from the plant, the pipeline going to the system, the compressor to get the gases up to pressure, the pre-water gas shift, and completely on your right, you see the CWEX column, and for scale, you can also see the pre-water gas shift next to it. So what did we achieve in the Stepwise project? Over 5,000 cycles, we have shown that we can reach a CO2 purity up to 95% and a carbon capture rate up to 100%. And also we proved that we can achieve a cost reduction compared to the state of the art of 28%. So this was for us really a milestone to really demonstrate that we were not able to capture the CO2, but that it really is working in a very nice way and that we are competitive to the market. So then we had a follow-up project, the Fresme project, where we used the same installation, but where we wanted to demonstrate that the hydrogen and the CO2 that we produced was of such a quality that if you would want to go for the utilization option, this would be possible. In the Fresme project, we went from utilization to methanol. And the idea behind it was to use the methanol for the shipping industry. And we used it for the ferry boat of Stena Line that sails between Denmark and Sweden. So here you can see in a graphic picture the idea. Your steel gases, you convert them to CO2 and hydrogen and convert this to methanol and use it for the shipping. So what did we achieve? We treated 570,000 normal cubic meters of blast furnace gas, and were able to produce 25,000 liters of methanol over a total operation time of 15,000 hours. This really demonstrated us that indeed the quality of the capture is in such a form that we can actually use it for utilization. And talking about utilization, this is also where I have another poll question for you listening at home. Looking at capture, utilization and storage, there is multiple of options. And I would like to know how you consider this. Do you think carbon capture and carbon utilization go hand in hand in the energy transition? Or are you of the opinion that carbon capture and storage only is an enabler for carbon capture and utilization? Or do you think there's so much CO2 in the industry that it really that there's so much that it's not really worthwhile to consider CCU? We will come back to this again in a short bit. In the meanwhile, I have some questions. And so that I'm not the only one speaking, I will, Erik was the project leader also for the other 2 projects. So Erik, you will know these questions as well. But I have a very nice question here is, do you need to put in extra energy in the process, or is the high temperature, or is the high temperature just a requirement of the process?
Okay, thank you for this question. The high temperature is indeed a requirement for the process because we combine the absorption effect with the chemistry of the water gas shift. And you also need the pre-shift to convert the bulk of the CO. So that's where you need the temperature for. Eventually, you need to add additional energy because that's the basic of every capture technology. CO2 capture always costs energy. So that's why it's also important for these kind of projects to demonstrate where you are with this with the energy consumption. And that's where the winners will be indeed with the most efficient use of energy for capturing CO2.
Okay, great. I have another question. I think this is a quick one to answer. Can you tell something about the pressure range for the adsorption desorption steps that we're looking at?
Okay, so indeed we have a pressure swing absorption process, as Soledad explained, meaning that the absorption takes place at increased pressure and the regeneration of the material is done with steam at low pressure. A typical range is a low pressure at 1.5 bar absolute, for example, and a higher pressure range in the order of 15 to 35 bars typically. So that gives you the working capacity of the material, and of course, depending on optimization of your OPEX, of your CAPEX, this pressure range can change. But that's typical pressure ranges. Okay,
great. I have more questions to come, but I think we'll see, at the end also how much time we have left. So there are some nice other questions coming around. So this was the history of, although it's very recent history, but so these were the projects, they were finished. But currently we have the Initiate project. That's a running project that's also around the stepwise technology for the steel industry. Erik, you are a project manager. Maybe you can shortly introduce yourself and tell us more about the Initiate project.
Yes, I'll gladly do that. So my name is Erik van Dijk. I'm a chemical engineer by background and working now at TNO for over 20 years. Currently as a senior researcher, but also project manager. So I'm leading the bigger projects on the development of the SeaWax technology. As Soledad explained, the Stepwise and the FreshMe project, but now currently the Initiate project. So I'll tell you somewhat more about the Initiate project, so the current status of the development of the technology in the next, roughly 10 minutes. So it's building on indeed the facilities we already have in Luleå at our partner in Swerim. So the Initiate concept is about transforming residual gases from the iron and steel industry into a feedstock for the chemical industry. And specifically, we are linking the BOF gases to the production of ammonia and urea. So that's the concept. In the light of the development of the SeaWax technology, this project will bring us towards a TRL7 demonstration of the technology. So what Soledad explained for the history, in the Stepwise and FreshMe project, we went to TRL6, and this project will bring the technology to TRL7, meaning that we will build a multi-column system receiving the real gases from the steel industry. Well, a multi-column system is because of indeed this pressure swing absorption operation. So a multi-column system would allow you to continuously produce a CO2 stream and a hydrogen containing stream. So somewhat more detail about the vision and the concept of the Initiate project. So we are linking the iron and steel to the ammonia and urea sector, and thus demonstrating the reuse of the carbon within the BOF gas towards urea. This demonstration, the project heavily relies on the demonstration of the technology, so demonstrate the operational reliability to be ready for the commercialization. And we do that by demonstrating the continuous production of ammonia from BOF gas. And with that, we aim to demonstrate that this gives you a positive business case at an internal rate of return of 15%. And of course, you need a strong consortium for this, which is depicted below, and I'll talk about this somewhat later. So let's go a little bit deeper into the concept. So what you see here in this slide is block flow diagrams, very simplified block flow diagrams of the two industries we're looking at. So on the left-hand side, you see the iron and steel industry taking in iron ore and coal, and eventually, of course, producing steel products. That's their core business. During these processes, valuable off-gases are produced containing caloric value. So they are used internally to some extent, and the surplus of these gases is normally sent to a power plant, where you have the major part of the CO2 emissions. Well, 50% actually. On the right-hand side is a block flow diagram of an ammonia and urea plant. So normally taking in natural gas, doing the reforming step, cleaning the syngas up to a hydrogen-nitrogen mixture, do the ammonia production, recombine it with part of the CO2, and then you come to your urea product. Well, there's also CO2 emissions involved in this process. So both of them indeed have a certain carbon footprint. So typically 2 tons of CO2 per ton of hot rolled coil for the steel industry, and typically 1.8 ton of CO2 per ton of ammonia product. So both industries naturally are exploring ways to decrease their carbon footprint. For the steel industry, you could replace the reductant, which is coal in a standard plant, towards natural gas and hydrogen, so go towards the DRI route. You could apply CO2 capture technologies, naturally. There's also a trend of going towards more scrap in the mix, and there's trends to increase the efficiency of iron and steel making, for example, with the HySana project. For the ammonia and urea industry, they are also looking at CO2 capture, but also using ways of using green hydrogen, so taking nitrogen from the air, combine it with green hydrogen for your ammonia production, but then you still need a carbon source, a CO2 source for your urea. Well, and in the Initiate project, we are looking at the symbiosis options between these two industries, and that looks in a simplified scheme like this. So we plan to use the BOF gases from the steel industry as a feedstock for the ammonia and urea production. And why BOF gas, you might ask? Well, it has a very favorable hydrogen and nitrogen content. So if you do the complete conversion and the CO2 removal, the ratio of hydrogen and nitrogen is very suitable for the ammonia production. So that's why we use this gas. So this is the concept we want to demonstrate. And there's 2 enabling technologies on this sheet. One of it is the CWEX technology, sorption osmotic shift, that we're talking about today. And the other one is the ammonia production, where we will demonstrate a novel concept focusing on substoichiometric feeds of hydrogen and nitrogen. Well, the Initiate project is born out of our development in the Stepwise and the FreshMe project. But prior to the Initiate project, we did a pre-feasibility study where we looked at the technical, economical, and environmental aspects and benefits that this route could have. And there we identified that there's definitely technical feasibility by means of these two enabling technologies. So sorption osmotic shift and the substoichiometric ammonia loop. The study towards the economical feasibility showed that there's a positive business case if you go for urea derivative products. So that actually means that combining these two industries via this route actually pays for the capture of the CO2. And very importantly, for the economic feasibility, early on we have already identified that there are locations within Europe where BOF gas is available close to an ammonia and urea plant, which is of course essential for the rollout. Environmental benefits have been identified, and that's shown in this right-hand graph. So on the complete right, what you see there is the CO2 emissions from the two reference industries separately, but added up. So, and then you come to 100%. If you apply the initiate concept, you already see that you save about 70% of the CO2, which means that you are 70% less carbon intensive. And if you then combine that with the potential of the storage of the sequestration of this captured CO2, you can even decrease your carbon footprint by 70%. And another very important result from this feasibility study is that we were able to build a strong consortium for the next, for the follow-up project, which is Initiate, and that has started now. So in Initiate, we will demonstrate, validate, and do all the preparations for the first-of-a-kind plant. So to come back to the consortium that we built, here you see the partners, and we are convinced with this consortium that we span the entire value chain from material and equipment suppliers through technology licensors and two big end users, being ArcelorMittal and SSAB. And with the backup of knowledge support in the form of universities and Radboud University and Politecnico di Milano, together with CO2 Value Europe. So we have a 5-year project, started in November 2020, and a subsidy from the Commission of 21.3 million euros. So Initiate will result eventually into the evidence for the rollout. So beyond the demonstration, we via value engineering and integration, we will show that we can reduce the cost and reach a certain IRR. The project will also show the bankability of the pre-FEED. And make all the steps for the first-of-a-kind plant as the next step at a selected site. Because of the dynamics of BOF gas and ideally the most stable operation of the ammonia as possible, you need to have quite advanced control. So we also developed that within the project. And next to these technological goals, we will also look at quantifying the social, economic, and environmental impact of this industrial symbiosis route within the European context. So where are we now? As said, we started in 2020, so we're now in month 18 of the project. A very important aspect in the beginning of the project was the engineering and procurement of the pilot that we are going to build to demonstrate the concept. So the layout and the functional materials have been fixed, and the control architecture characteristics have also been fixed, and this is now in further development. And this depends, of course, on the dynamics of the feed, but also the contaminants that you can expect in these kind of feeds. In the project, there's a very strong contribution of multi-scale modeling, because, for example, for the control. So we are developing dynamic models for all the unit operations in the plant. And for the validation of the technology, we need the techno-economic evaluations and the life cycle assessment, as well as the symbiotic analysis. So for these analysis, the basis has been made. For the commercial implementation plan, the basis for the business modeling has been defined, and we are progressing with the site identification. So, initiate in a nutshell, we will demonstrate the reliability of this route by the continuous production of ammonia, and also confirming the business case at the end of this project with, again, this consortium. And I should mention, we're also backed up by our esteemed members of the External Advisory Board, the World Steel, Fertiberia, OCI Nitrogen, and STEP. And that more or less summarizes the current status of the project.
Yeah, thanks. So this was, until now, we have covered history, present, and before we go to the future, we have some time to go at the poll questions, but also to have some questions from the audience. But first the poll questions, and maybe ask Carlo already for some feedback. Carlo, we just asked the audience how they look at carbon capture versus carbon capture storage versus utilization. And 37% of the audience thinks that CCS and CCU go hand in hand in the energy transition, so that we need them both. Is that an outcome you would have expected?
Yes, it is. I think the CCU and CCS shall go hand by hand to better contribute to the energy transition, as we can combine the benefits from the utilization of a suitable part of the carbon captured, along with the transportation and storage of the remaining. Yes, I deem they shall go hand by hand.
Would have voted exactly the same as the majority of the audience. I think yes.
Yes.
So, to give an idea so that you know, 70% thinks that it's an enabler, and the minority, so only 9% thinks that there's too much CO2 in the industry to really consider CCU. With the story you just told, Erik, I have some questions that came up. There's one that I might not even ask to you. Maybe I can answer that myself. There's one question on why are we only focusing on the iron and steel industry for now? That is, so like I told in the beginning, we think CWEX is really a platform technology, but the projects and the advantage that we saw, we're really focused on the iron and steel industry because that's one of the hard to abate industries where also we were able to get the projects to show that the technology is working. But the lessons we learned from the iron and steel industry, we think, are also really helping to integrate the CWEX technology in other industries. So yes, the focus now is on this, but that's because we also have the projects in the present, and also the projects we did were in the iron and steel industry. So that is why you see us telling about how we demonstrated there. But Erik, you agree this not translates one-on-one, but it really helps also for the implementation in other industries.
Yes, the lessons we learn indeed in this rollout in the steel industry, they can be considered as general lessons. So, for example, what is very difficult to demonstrate on lab scale is the heat management of these columns. So you need to go to bigger scale there, and then actually the feed gas you get doesn't really matter that much. It's really the scale that matters. So we have been talking now a lot indeed about the steel industry, which does not mean, as you also indicate, Soledad, that's definitely not the only industry we are looking at.
No, thanks. Good to clarify that. I have some questions which are fun to do because they're really technical, so I'll ask them to you. So in chemical processes, there's also quite often impurities in the gases. Can you tell a bit how the technology handles these impurities?
Yeah, that's a very good question indeed. What we have demonstrated in the Stepwise project is that we can deal quite efficiently with the impurities which are in normal blast furnace gas. And the main impurity there is sulfur in the form of H2S and COS. Both the pre-water gas shift section as our technology, the sorption-enhanced water gas shift section, uses materials which can deal very efficiently with these contaminants. And what we actually demonstrated is that H2S and COS are actually removed from the gases together with the CO2. So it's a reversible interaction with the solvent, and it ends up in your CO2. So you decarbonize and desulfurize these kind of streams. Now, in the Initiate project, we are using a different gas. So that's the basic oxygen furnace gas, and there's somewhat more types of contaminants present there. And we are currently looking into the effect of those, but up to now we have not seen any showstoppers for the material.
So very robust technology.
Yes, we think
it
is.
Good to know. The next question I have, which is, I also think it's an interesting because it's also telling, that CWEC's just part of the chain. But if you really want pure hydrogen, so you would need maybe some purification after the CWECs as well, right?
Yeah, that's true.
Can you tell a bit about that? How that would look like, or
Sure. Indeed, the materials we use in the CWECs column, they typically interact with sour components, and in syngas there are components that don't meet these criteria, and they are considered as inert and simply pass together with the hydrogen. So, for example, for a blast furnace gas feed, there's a significant amount of nitrogen in there, and that ends up indeed in a hydrogen product. So if you want to go from steel gases to pure hydrogen, you still have to purify the hydrogen afterwards.
Yes. Okay, good. Excuse me. Okay. Let me see. I think that for now, that's the questions I think I want to ask you, Erik. So I would like to go to the next part, and that's the future of one of the possible futures, but it's the future we're talking about now. And Carlo Morelli is an innovation ambassador at Polworth. He's going to tell a bit more about that. So Carlo, please introduce maybe yourself a bit more, but also tell us and the audience a bit about what we see as the next steps for this technology.
Yes, thank you, Soledad. And for this invitation, thank you to all participants for joining us. My name is Carlo Morelli. My background is automation and process control engineering. Then I developed during my career as a technical coordination project management of R&D projects in general. My role of innovation ambassador is in Polworth, Italia, is concerned with investigations, analysis, critical review of existing market solutions and new technologies to act as a, let's say, senior advisor to the high management for the application within the iron and steel industry. I would also recall that Polworth is part of the SMS group. Let's start, please, with the next slide. So I would show you how we can improve the CO2 reduction impact within the iron and steel industry. So, as already mentioned, the background is well known to everybody. We have to cope with the global climate challenge and take care of suitable decarbonization roadmap to reach the ambitious targets, European and worldwide targets in the next decades. An important point to consider is, of course, the decarbonization of hard-to-abate industries, such as the iron and steel sector is. And Paul Wurth is concerned with these specific sectors. The iron and steel industry has peculiar characteristics, such as large volumes of process gases containing CO2, which can therefore be treated by specific applicable CO2 capture technologies. A second point to consider is that currently the availability of hydrogen as an alternative fuel is insufficient to replace the full routes of iron making. I mean, of course, alternative with respect to the carbon-based fuels. So we have to take care of a transition period where we have to reduce the CO2 impact to maintain the actual production routes and the competitiveness and the environmental compliance of the existing industry. And the market pressure from the emission trading scheme is, of course, highly affecting the industry competitiveness. Based on these considerations, we shall study and identify how we can enable the sustainable green steel production in the next future. We can then consider the application of COX-based CO2 capture plants within the iron and steel plant. SUX as a pre-combustion CO2 capture technology is applicable to various process gases from iron making, such as the blast furnace gas, the direct regression gas, or basic oxygen furnace gas. The next slide, please. Then Paul Wurth identified CUX as a competitive CO2 capture technology within iron and steel works. And with respect to other possible CO2 capture technology, we identified for this technology some beneficial core features to be considered. They are the pre-combustion versus post-combustion, the absorption at high temperature, and an optimal thermodynamic equilibrium. These characteristics, which can convey the profitable quality of the outlet products, has also some positive economic advantages, which are basically the lower CAPEX, lower OPEX, and lower specific energy consumption for carbon avoidance. The next slide, please. Based on this consideration and our market expectation and vision of the carbon capture deployment with these iron and steel plants, we, Paul Wurth and TNO, signed a cooperation agreement to further scale up to the technology level of the core technology, of the CUX core technology. So to design and deploy CUX-based CO2 capture plants within the iron and steel industry, both for the blast furnace and basic oxygen furnace route and the direct reduction route. This shall enable, as I mentioned, a transition period, some probably decades of operation with existing plants, but with a very significant impact on the CO2 reduction, thanks to the adoption of SIUX-based CO2 capture plants. We need a further step to reach TRL 8 based on the industrial scale demonstration of the core technology. So a key point of our cooperation with TNO is design, construction, and test campaign of an industrial scale SIUX demonstration plant integrated within a steelworks in operation. We deem, and we made some preliminary studies, some feasibility studies, some considerations, preliminary simulation together with TNO to establish a suitable capacity, which is about 50 kilotons of captured CO2 per year, aimed at reaching the above target. During our preliminary consideration, we could, through simulation and preliminary studies, estimate the input and output figures expected for this demonstration plant that we plan to develop in the next future. The next slide, please. Based on this ambitious target, the future perspectives we expect are therefore an important contribution to the decarbonization of the iron and steel industry, thanks to the integration of SIUX-based CO2 capture technology within the existing iron and steel plants. We consider that the full CCU and CCS chains shall be applied and managed in order to combine the benefits from possible utilization on site of the captured CO2 according to reasonable amounts and transportation and sequestration for the remaining part of the captured CO2. By taking into account that on such plants, on such industrial sector, the potential amount of captured CO2 is considerably high. We might talk about millions of tons per year. So a future full-scale integration of this technology with the iron steel plants will be therefore applied, and with a future target of a green steel production in Europe and worldwide. That's all, and thank you so much for your attention.
Thanks, Carlo. I was too quick to already thank you, but thank you so much for this. With this, I have a few more questions for Carlo and Erik to finish up, and we're closing the end of this webinar. Carlo, I have one question for you. So CCS and SIUX in particular, you consider as one of the technologies for green steel making in the future. You think how will this also will be related to things like electric arc furnaces? That's a question coming from the audience. Do you see how will these technologies compare or grow side by side with each other?
I presume we can consider different production routes, and the targets are different. We can on one side contribute with electricity, so electrical arc furnace-based production, but considering the currently existing, I expect the amount of required steel and in particular of green electricity to feed a possible large set of electrical furnace-based plants. This is not expected to be the only solution in the next 30, 40 years. We can estimate that the transition to complete electricity may be enabled in a mid or long future. In the meantime, we have to cover the production requirements and the low H2 availability with existing blast furnace and BOF routes by enabling suitable CO2 reduction on these plants. So we have to keep in consideration two parallel routes, two parallel steps.
Yeah.
And we have to cope. We have an important role to reduce CO2 by deployment of CO2 capture plant within the existing plants.
Yeah. Thanks, Carlo. I think that is clear. I think that also goes hand in hand by the questions we got where we ask, how do things fit in? Or we asked the question in the beginning, do we see it's just only for the transition period? Or is it also something for the future? And a lot of people think indeed that it's for the transition period, very interesting carbon capture, but also after that. So thanks, that links to it, very nice. Erik, one final question to you, and that's about the Initiate project. It's a question about how often urea plants and steel plants actually are close enough, because we think to really do transport through pipelines. Is that, for something very common or not? Can you give a bit an idea on how often this symbiosis is occurring?
Yeah, I can shed some light on that. I cannot give you exact numbers, but there's multiple sites, even within Europe, where these two industries are sufficiently close to each other to indeed consider pipeline transportation of either the hydrogen nitrogen product or the BOF gas as such. So there's really multiple rollout options within Europe, for sure.
Okay, that's great. Looking at the time, I would like to come to the end of our webinar. What we try to show you here is that our SeaWax technology is advancing rapidly. We're making huge steps in the last years to really demonstrate that this technology will get us to a more sustainable industry. Today, we indeed put a lot of emphasis on the iron and steel industry, and we're very proud to show you how the technology is working there. But if you're looking at this and you think, hey, this might be interesting also for our application, please feel free to contact us, because we think that we really want to build together on this technology. A lot of questions came in that we did not have time to answer. I think what we will do is maybe come with a short Q&A and maybe post it on the website. We'll see about how we will do that, but we will try to answer as many of the questions you had as possible in a later state. If you want to learn more about SeaWax, two ways you can contact me directly, so through the content information you see here, but you can also visit the website of TNO. And if you search there on SeaWax, you will find all the information that we told here today and even more. I would like to thank Erik and Carlo for joining me. And of course, people at home, thank you so much for joining us, and love to see you in the future. Bye-bye.